Welcome to Clustering on Manifolds via mode hunting on first principle nested spheres components after linkage clustering. That's a long title. This is joint work with Benjamin Elsner, Hendrik Wiechers, and Conti Mardia. Mode hunting via smoothing with statistical guarantees, which means causality, for example, that if you smooth, you do not add any more modes, seems only possible in one dimension, by Gaussian smoothing on the line or wrapped Gaussians on the circle. Clustering can be done on a Euclidean space very easily for two distance clusters if you do PCA. Then, hopefully, looking at the modes, these clusters separate on the first PC. This example with 3 clusters, you would probably have 3 modes. But if cluster number 3 would be placed more unfortunate, you might do something else, for example, hierarchical linkage clustering. Below you see such a linkage clustering tree. It gets more complicated if clusters have different densities and are non-Gaussian. So we still do our clustering tree with clusters 4 and 5, but if we do a cut, say this red line, then we can nicely separate clusters 1 and 2 on one side, cluster 1 and 3 on one side, and cluster 2 on the other side. But at this height, we would cut cluster 4 in many pieces. So we suggest to do this adaptively. So cluster the high density clusters first, and then in a second step do the low density clusters. Call this adaptive linkage clustering age. How would we separate the cluster 1, Roman 1, which consists of clusters 1 and 3? Well, either we could do more iteration of age, or not do linear PCA, but do PCA with a circle. If you see the circle here, we project the data to the circle, then cluster 1 is at the northwest side, and cluster 3 is on the southeast side. Notably, if we do classical PCA in n dimensions, the space of first PCs has dimension 2n minus 2, whereas the space of circles and lines has dimension 3n minus 3. So we gain 50% of freedom. Why at all circles? Well, this comes from the fact that we were looking at RNA and protein data. We model them by dihedral angles, so along every bond you have an angle. If you have n bonds, you land on a torus. Every angle is from 0 to 2 pi. And if you're in the torus, even if you want to do PCA, geodesic PCA, this seems to be a bad idea because every data set can be approximated perfectly by a line. Winding line, if it has irrational slope, it winds around infinitely. People have tried to do some tangent space PCA, but that misses periodicity. There is dihedral PCA around, which does the following. You embed S1 in R2, which means every PC is effectively 2D. So we can't do good mode hunting on that. Others have tried just to allow only directions that don't wind too much around the torus. But that's a very low dimensional family. So Conti Mardia asked me some 10 years ago, how do you do PCA on a torus? Well, the geometry is pretty vicious, so I asked Benjamin Elsner to invent a new geometry which is less vicious. And he suggested to turn a torus into a stratified sphere and do stratified principal nested spheres on that. Very recently, Hendrik Wiechers, who's a PhD student, turns any space into a stratified sphere and does stratified PNS there. So what is PNS? Start with data on a sphere. You approximate this data by the best n-1 dimensional subsphere in the sense of sum squared to spherical residues. Then you project your data to this n-1 dimensional subsphere, and within that n-1 dimensional subsphere, approximate the data with the best n-2 dimensional subsphere, and so on until you're left at 1 dimension. And this circle, the S1, is then your first principal nested sphere component. This is a perfect analogon of Euclidean PCA, namely that the first PC is the result of nested higher dimensional subspaces. And in Euclidean PCA, nestedness comes for free. Here on spheres, we have to require it. Now, Sanchu Yang discovered you could actually use small spheres as well, giving you this plus 50% of flexibility. So principal nested small spheres. This requires some statistical testing against overfitting, namely fitting data with a small sphere where maybe a great sphere might be more appropriate. Now, how do we get from a sphere to from a torus to a stratified sphere? That's the sausage transformation. You start with a torus, here everything for a two-dimensional torus. You cut it open, then you wrap up the two ends, you connect them to keep periodicity, and you come up with something like a sausage, a kielbasa, which is a sphere topologically with north and south pole identified. In higher dimensions, things get a little more complicated. We do, among others, an identification along an n-2 dimensional subtorus. Now, how do we put this into action? If we're on a Euclidean space, we pre-cluster with any favorite methods, for example, age. Then we approximate every pre-cluster with a sphere and map the pre-cluster to it. On this sphere, we perform circular mode hunting on the first principal nested spheres component. This gives us some post-clustering. And this requires, of course, some significance of circular modes via smoothing with wrapped Gaussians. For shape data, you would just pre-cluster as above. We're on a metric space. Then you map the clusters to horizontal slices, say through a Procrustes mean. If we do shape analysis, we are already on a sphere. If we do size and shape, we'll map as before the data to an approximating sphere, and we proceed as above. Or for torus data, clean mintage, as has been presented by Henrik Wicher's talk, does this for tori. So MINS works as follows. First step, pre-cluster as you would be on a metric space. Map every pre-cluster to a data-driven, possibly stratified sphere. Perform principal nested spheres on every pre-cluster and do mode hunting on the first principal component. This gives you your post-clusters. Here you see an example of RNA backbones. On the left-hand side, the black thing is one of such clusters we obtained. And if we do mode hunting on the first principal nested spheres component, you see the colors giving 4 subclusters. I'm not saying this is the method solving all clustering problems on a manifold, but it does solve quite a few. As Steve Marin puts it, every dog has its day. Thank you very much, and I conclude with references.